We are what we call separable differential equations. And so different types of differential equations that we can solve. Something is separable. We've got some function of y, some function of x. To separate it, the idea is that we want to completely pull apart the y function and the g function so that we can integrate with respect to y, we can integrate with respect to x. So if we have our differential equation is in terms of both y and x, we could turn this into 1 over that function of y times dy, which we could then integrate because we're y in terms of y, and then we would have g of x dx, and we could integrate to solve. That is not a whiteboard marker. Take something. Y dx equals xy squared. I can rewrite that. Straightforward. X squared, y squared. And so we've got the product of something in terms of x, the product of something in terms of y. It's literally separable. I can separate the x and the y easily. Turn this into dy over y squared equals x squared dx. Have dy over y squared is x squared dx. We can solve the differential equation. We'll take the integral of both sides. We're integrating a function of y with respect to y. And it's going to integrate just the same no matter what variable we have. It's going to be negative y to the negative 1. It'll be 1/3 x cubed plus c. And then I can solve for y. So y to the negative 1. Right on the desk. Thanks. Negative 1/3 x plus c. A constant divided by negative 1 is still a constant. So I'm going to take the reciprocal. So we got y equals 1 over negative 1/3 x squared plus c. X cubed. Oh, where did I switch? X cubed.
On camera. You can't make mistakes.
Let's get used to it. See my mistakes so far. Yay. Follow up. So that is our general equation, our general solution. We want to have an initial value solution. If we also pass through 1, 1, well, we've got an x, we've got a y, we can solve for c. Oh, no. 1 equals 1 over negative 1/3 plus squared plus c. It's going to negative 1/3 c equals 1, c equals 4/3. Given some initial value. Just make an x squared all the way through. 3. I don't know where I got the x squared from. Showing up backwards on my screen here. Everything's mirrored. But when you record, like looking at you, does it flip it back over?
No, I don't think so.
Uh-oh. Here you go, Esther. Have fun. Okay. How's that look? Good? Makes sense? Separate the values.
Let's hope Esther can read backwards.
Well, if you show it in the mirror,
Oh.
I think I can, like, in QuickTime kind of reflect things. But
We'll figure it out, won't we?
well, I'll figure it out. All right. Let's do. I needed that block. dy dx. Let's. Oh, I don't like this.
Okay.
Since when has a math teacher ever said that?
I want something more.
Oh,
Oh, God.
there you go.
Don't want that. Alright. dy dx equals x cubed y passing through 0, 2. Separate the variables. dy over y equals x cubed dx. Integrate both sides. Maybe see why I wanted just y. Integral of dy over y is ln of y. Okay. We've got x cubed, so that is 1/4 x to the 4th. Don't mess up the power rule. Plus c. Solve for y. We've got that ln of y. And ln of y equals e, the 1/4 x to the 4th plus c. I'm going to manipulate this a little bit more before using that initial value. We remember properties of exponents. Adding an exponent, this is like e to the c times e to the 1/4 x to the 4th. reason I do that. E to some exponent c, that's just a constant. That's just a constant. So we got constant times e to the 1/4 x to the 4th equals y. There's our general solution. Is that okay so far? Questions, concerns?
Concerns.
Okay. What can I help with?
Well, yeah, why do you have to bring the C down?
I don't. It gives me, think about our exponential growth or decay problems. Exponential growth or decay, how we've seen it in the past. We've got some initial value, we've got e raised to our exponent. That really gives us our initial value, kind of what happens at 0. Population growth, you have the population at time 0. We don't need to bring it down. I'm gonna bring it down because now when x is 0, it's gonna be e to the 0, that's just gonna be 1. And so my c is gonna be the 2.
I solved for c at the ln of y equals 1/4 x to the 4th plus c stage, and it kind of was easier to see. Like,
Okay.
to pull down c, so I don't know if people want to do that instead.
Let's do that instead. Let's do that. Pause on that. Let's come back. So now you're saying, so here, we've got x is 0, we've got y is 2. So we've got natural log of 2, that's gonna be 0 plus c. So ln of 2 equals c. Okay?
Yeah, that's what I got, but I kept C up in the.
Okay.
So will it still be the same if I put natural log of 2 in the exponent?
Let's check. Let's do it both ways. If we have this, and now if we rewrite it, we have our e to the 1/4 x to the 4th plus ln of 2 equals y. That addition, that's going to be y equals e to the ln 2 times e to the 1/4 x to the 4th. E to the ln 2, e and ln are inverses. We've got 2 e to the 1/4 x to the 4th. So by solving for c before, we've got this, but we can also pull it apart, simplify it a little bit. So we've got 2e 1/4 x to the 4th. Where I was going, I had y equals c e to the 1/4 x to the 4. If x is 0, we've got e to the 0. E to the 0 is 1. 1 times c equals 2. That would give us c equals 2. And we have exactly the same thing. So the manipulation, it's going to give us exactly the same thing anyways. Going back, maybe that's a little bit better. Our general exponential value, where you've got your base to the x, we've got some constant, some initial value. So, like when we're graphing, it was always 0a was our initial value point when we're graphing exponential equations. So that's how it also comes out. And moving it around, we've got that. Big idea here, we've got that ln. We might need to use our exponential form to switch it back around.
Yay.
So fix concerns, okay? Other questions?